Right, what questions do we have? Which one? 12. In Rutherford's scattering experiment, an alpha particle of charge of 2e heads directly towards the lead nucleus of charge 82e. The alpha particle has a kinetic energy of 5.3 mega eV when really far away from the nucleus. Assuming the lead nucleus is fixed in space, determine the closest distance in femtometers. Hint, use conservation of energy. All right, so reminder, what's conservation of energy? What equation should I be writing up here right now? I would start at actual conservation of energy before you launch into any specific equations. And that is just simply just the kinetic energy initial plus the gravitational initial is equal to kinetic final plus gravitational final. A gentle reminder, this actually is going back to a problem we did all the way back in electricity. But what is your equation for potential energy of electric?
Isn't it like KQQ over R?
Yep. There you go. All right. Which of these cancel?
The gravity.
No, you can't cancel both. Look at your equation over there. That equation over on the right side should tell you when that cancels. Let me say that differently. Look at that equation and tell me when is that equation going to equal 0. Use any amount of calculus or pre-calc knowledge right here.
Wait, what'd you say again?
That equation over on the far right side, UE equals KQQ over R. When is that going to be 0?
Whenever the charges are 0?
What's that?
Whenever the charges are 0?
Well, that doesn't make, I mean, sure, but also then there's no potential energy. We know the charges aren't 0.
Whenever the charges go to infinity?
Correct, when they're very far away.
I mean,
so, does the problem tell you a spot in which R is particularly very large?
Infinity? So number of infinity?
Is that at the beginning or the end? So it says kinetic energy of 5.3 when very far away, right? So that would just be initial is 0. I guess initial final doesn't much matter specifically here, but just pick a spot. When it has this kinetic energy, it has no gravitational because R is very large, because as you take the limit as R approaches infinity, potential energy would be 0. This is going all the way back also to something that we said back in electricity, which is at infinity is when energy is 0. Okay, one other thing up here cancels. What is it and why? Let's draw a picture if we haven't yet already. We have lead over here. I'm not going to draw all of the 82, but here is the lead nucleus, which has a charge of 82e. It says that right over there, 82e. Of course, 82e, you could have found that yourself, because what about lead would tell you that it's 82e? 82, correct. 82 is its atomic number, okay? So now over here we have a helium or alpha particle coming in with a charge of 2e. What are these going to do to each other as they head in there? Repel. So what other thing up there is going to cancel? Yep, kinetic energy final. Because it asked specifically when is it going to get the closest? Because that's V1 and that goes to 0. From here, do we need to fill out this equation?
Like fill out as in like.
Do we need to write 1/2 mv squared?
No.
Why not?
Because it gives you.
Because it straight up tells us kinetic energy. Correct. So here we go. I have kinetic energy initial is equal. What equation should I use over here? And what am I solving for?
Radius.
R. Not radius per se. And there it is. K, of course, is 9 times 10 to the 9th. One of the Q's it said was 2e. The other was 82e. And divide by Ki, which is, it said, it's a red, isn't it a red number? Yeah, it's a red number, but 5.3 mega EV. Plug and chug, and you should have your answer. Now, keep in mind that does ask for the answer in femtometers. If you don't remember femto, yeah, don't forget that the SI unit, well, any SI units, if you don't remember, milli, micro, nano, pico, I think femto is -15 if I'm not mistaken, but look it up in your sheet, and it'll tell you. What's that?
It's not on the sheet. It only goes to pico. I had to Google it.
Is femto -15?
Hopefully, because it goes up by 3.
Well, there's a. What do you mean? Hopefully, you thought you said you googled it.
I did Google it. It's -15, but I
Yeah.
don't have it in front of me.
There you go, -15. All right, so I'm writing in 9e to the 9th times 2. Technically, one of those e's could cancel, but I'll just put it all both in here. Times 82 times 1.6 e to the -19th squared, because I'm doing both e's collectively. And then I divide that by 5.3 times, well, hold on, put that in parentheses.
Can you square the e's right?
I didn't, because there's, yeah, I put both of them in there. But yeah. E to the 6th times 1.6 e to the -19th. So actually, if you wanted to, like I said, you could cancel one of those e's with one of those e's, but if you don't spot that, it's no big deal.
I got to the
And
negative. Oh, wait, never mind.
I have 4.46 times 10 to the -14th. And what simple thing do I need to do to put that in femto? How do I put that into -15?
We just take off the -14 and move the decimal.
To get to -15, do I have to go up or down?
You go up. You go up.
Try again.
Go down.
-15 is smaller than -14. So I go down by 1 decimal place. So how do I make it the same number? If I just made this side go down by 1 decimal place, what do I need to do over here?
You would then.
Make it get bigger by 1 decimal place.
Yeah.
And so now we have 44.6 femtometers. For me, anyway. Let me check to make sure I'm right.
See, my first answer is still in the -33rd, and I don't know how.
Okay. What elements are you using?
Mercury.
Okay, so what's the charge on? Well, I'm sorry. Mercury, Hg. And it says it's 80, right? I mean, it says it right on there on your problem. It tells you right next to it what the charge is.
And you got to the what power?
-14.
Yeah, it is maybe 14.
So you got 9 times 10 to the 9th times 2 times 80 times 1.6 e to the -19th squared divided by, what was your kinetic energy?
5.4.
Mega EV.
Yeah.
So I'm dividing by 5.4?
Mhm.
5.4 e to the -6 for the mega, sorry, +6, my apologies, for the mega. Now because that's e, I'm multiplying by 1.6 times to the -19th there, and then I'm being very careful with my parentheses on the bottom.
That's okay.
And your answer was 4.27 times 10 to the -14.
Okay, I fixed it.
Cool.
I might need help.
Sure. What's your element?
10.
You have 10, you said? So you're what, SN 50?
Yeah.
Okay. So you're writing 9e to the 9th times 2 times 50. Excuse me. Times 1.6 e to the -19th squared. Divided by, what's your kinetic energy?
5.1 negative.
5.1 e to the 6 times 1.6 e to the -19. I have 2.82 times 10 to the -14.
Can I just look at my calculation? See if I'm getting to the -33rd.
So to get the mega electron volt, which
Oh,
you need
so
to
I just put 1.6 whatever on the bottom.
times, yeah, 1.6 e to the negative 19th. There.
Thank you.
All right, next question.
10.
10. Okay. An electron has a de Broglie wavelength equal to the diameter of a hydrogen atom in its ground state. Okay? What is the kinetic energy of that electron? All right, so it said that it had what was it? The wavelength is equal to 2a0, where a0 is equal to that number it gave us. 0.0529 nanometers. Yes?
Yep.
Okay. Now, if you'll remember, that equation is equal to the wavelength is equal to h over momentum, right? So with this equation right here, you can figure out what the momentum is, or if you prefer to find the velocity, that's completely fine. I will tell you a quick trick. If you don't know the quick trick, then what you're going to do is you're going to solve for velocity. You're going to go h over mv, and v is equal to h over m times wavelength. And with v, you're just going to simply plug in right there. You're going to get kinetic energy. Okay. That being said, here is a quick trick that is nice. I think that we've done this before, but we're going to definitely use it next chapter. So here it is real quick. Kinetic energy that you're used to is 1/2 mv squared. Yes? Okay. I would have everybody pay attention to this just real fast because you're going to definitely want this for next chapter. What I'm going to do real quick is I'm going to put an m over m here. So I'm going to square divide by m. Okay. And you'll see that hopefully those are in fact the exact same thing. Right? Just putting a m over there. And this is going to get me that this is, right here, it's the same thing as momentum squared over 2m. Yes? Have we seen this before? Yes or no? Okay. This equation right here is nice because it means we don't have to do that extra step that you saw just a second ago where we go find the velocity and do all this extra stuff with mass. And you'll see us use that a lot, and it relates momentum and kinetic energy directly. This is my preferred method, but like I said, what I would do here is just this, P equals h over wavelength, and I would go straight there. If you don't like that, especially if it's a test tomorrow and you're not sure, then you're going here to find velocity and here to find kinetic energy in one extra step. And then when you punch that in, you'll remember that the ground state of an electron is what? Yep. So just use EV. So using that to compare, as you can see with my work just a second ago, I believe it should be, I don't know, the red numbers might change things a little bit, but I'm pretty sure all of the answers are going to end up as about 10 times. Oh, never mind. There's no red numbers. There you go. So 10 times larger. Do we need me to go further beyond that?
No.
Okay. Next.
17.
17.
Part B specifically.
Conservation of momentum here.
For part B.
So, just so I can remember quickly here, my apologies because I know you don't need it, but an electron makes a transition from 4 to 2 in Bohr's orbit, which of course tells you that it's just a hydrogen. Going in that way, determine the wavelength in that particular process. Okay, so you're going to, of course, get negative 13.6 eV. Let's see here. Final minus initial. I always struggle with this, but yeah, 2. So final should be 4 minus initial, but of course it's minus a negative 13.6 eV. And I think it ended at 2, started at 4, so that should be 16. And since it's dropping down, should that be negative or positive? Not that it particularly matters, but I think it's important to keep track of. It should be negative, yes, because it's losing that energy. Of course, when we do this, just as a heads up, because some people are confused by this. This is the energy lost by the atom, but of course, conservation of energy says it's going somewhere else, so that's kind of confusing because it's the atom that's losing energy. It is then the photon that is gaining that exact amount of energy. So, of course, this is the amount of energy, which is 13.6 divided by 4. So I got 2.55 or negative 2.55 EV. Of course, set that equal to HC over lambda. Lambda is equal to HC divided by that 2.55 EV. Notice my switch from negative to positive here because that's talking about the atom and this is talking about the photon. And I get a wavelength, and I need to know the wavelength, which is why I'm doing this right now. 6.3 nanometers. Okay, now to draw a picture for part B, here's what we essentially have. We have this hydrogen atom over here and a photon kicked out that way. Terrible picture. Let's see if we can do a little better. Okay, a photon kicked out that way. So what it tells you is it tells you that the atom is initially at rest and then says what should it be afterwards. The fact that they start at rest kind of clues you into the fact that this should be a conservation of momentum thing. So what we have here is this: conservation of momentum initial, conservation of momentum final. And this is before and after the collision. So this is the momentum of the photon. What's a good thing to use for a photon? Sure. Plus momentum of hydrogen, and both of those are initial, is equal to the momentum of photon final plus the momentum of the hydrogen final. And which of these are 0?
So that would mean hydrogen initial.
Hydrogen initial is 0. What else is 0? Did the photon exist prior to this dropping down?
No.
So I'm going to go ahead and say, since it didn't exist, it's fair to say that the initial momentum of this is. So essentially, here is the problem on a grand scale. Okay, here's Spainauer standing in front of you with the marker in his hand. Okay, he has a momentum of 0. This is a momentum of 0, and then he takes this marker pen and throws it that way incredibly fast. The incredibly fast part is important. What do you expect to happen to Spainauer? Push back the other way. How should their momentums compare? No, try again. Sorry, my apologies. Close. Close. Yes, well, not inverse what you're saying. Equal and opposite, correct. Okay, how should their velocities compare? Obviously, you'd expect this one to be a lot faster. Why do you expect this one to be a lot faster in momentum? I have way more mass than it, right? Now, up here, it's a little bit tricky, of course, because. So, here's the math, real quick, of what we just said. The momentum of the hydrogen final is going to be equal and opposite to the photon. And see previous conversation. How do you calculate the momentum of the photon?
The momentum of photon MV.
The
momentum of a photon.
Out of a photon, you can't do MV. Why can't you do MV for a photon?
Because it's on and on, or it's a very, very tiny. It's moving at the speed of light.
I'll write it out for you. Okay, that is, by the way, how you find the hydrogen. Why can't you use that for a photon? Mass. What's the mass of a photon? It's light. 0. There is no mass of a photon. Does it still have momentum? Yep. Remember we talked about this with the photoelectric effect. Okay, we'll still have momentum. How do you calculate it? How do you calculate it? Someone, please. There it is. So this is equal to negative h over wavelength. So if you want to know the velocity, what simple thing do we do here? There you go. Now, you might look at this and go, Spainor, I don't know how to calculate the mass of a hydrogen atom. Yes, you do. Yes, you do. What is the mass of a hydrogen atom in essence? The mass of a proton. Why am I ignoring electrons? A proton is to the negative 27th. An electron is negative 31st. Now, while those are both very small numbers, are they comparable to each other? No. One is 1,000th the size of the other. So what is the mass of the hydrogen atom? The mass of the only proton it has, correct. So you should take h, which of course is a constant, divided by 1.67 times 10 to the negative 27 kilograms, times the wavelength, which we calculated just a minute ago on part A, is 486.3 nanometers for me anyway. Oops. Okay.
That's the wavelength?
Uh-huh.
Oh.
We had calculated that.
Yes.
Yeah. 6.63 e to the negative 34th divided by 1.67 e to the negative 27 times 486.3 e to the negative 9. Actually, I would argue that's surprisingly fast. 0.816. Let's see if I'm right. I would guess if you struggled on that one, it was just forgot that momentum is calculated as h over width.
Pretty much. I also didn't exactly use conservation momentum, but I was still using the same equations, which is
Gotcha. Yes. Next question.
I know it's a simple one, and I know I understand it. I think it's just the wording on it that's kind of tripping me up, but 20. By quantum numbers, that means the ins were, okay.
Yep. So,
Electrons.
the quantum number for electrons in the 3D shell, okay? Let's start off, I'll just walk through this very easy for you, okay? What does the 3 tell you? Which quantum number does the 3 tell you? Like when I write this over here, 1s, 2s, 2p, 3s, almost. For D, for F, this guy right here, what does the 3 mean? Or as you look on that chart, what does the 1 and the 2 tell you?
How far down the periodic table?
That is the principal quantum number. What letter is that? Oops, screwed up. N equals 3. What does the D tell you? I think that's what you were answering a minute ago. Subshell. So what letter was that?
L.
L. Okay. And what number is the D shell?
3.
Let's try this again. Let's do this. Okay. Remember with this rule, L can be anywhere between 0
Oh, no, I understand this.
and 1 minus that. So what I'm asking is, which of these specific numbers belongs with D? 2, correct. L is 2. Let's talk about ML. What does ML measure?
The amount of, possible numbers of
Yes. So it asked for the 3D subshell. Okay. So do we technically know which orientation specifically in? So we cannot say that we know ML at all. And then also, do we know the spin? No. Now, if you think about that, that makes sense because you'll notice that there are 5 orientations. And if there are 2 electron spins for each of those 5 orientations, that gives us a total of 10. And if you look at the periodic table and you count all the way from scandium all the way over to zinc right there, you will notice that makes sense because there are 10 possible options within the 3D subshell. So it kind of makes sense that that is all it was looking for, is that the principal number is n, and that the quantum, what is that number called? I always forget what the name of them is. I can get the letter, I can tell you what it means, which is the more important part, but it is somewhat helpful at times to know what those actually names are. Where are we at? Name of the number I am looking for is the orbital quantum number. There you go. And then the orientation is known as the orbital magnetic quantum number. And then,
but it says possible sets, so I'm like, is there more than N3L2?
Sure. Okay, so I got you. Okay, what are the possible sets of quantum numbers? For starters, how many possible sets are there? You're right. I screwed up. I should have one. How many possible sets, based on what I just told you a second ago, of quantum numbers are there? 10. So, in other words, let's talk about the sets that we can choose. Okay? We have n equals 3, L equals 2 for all of them. Okay? What's the first possible ML that there is? Negative 2. And within that ML is 2, what possible MS's are there? Yeah, I did it backwards, but same thing. All right, so there's your first 2 sets. So what you would have, make sure you're using copy and paste here. I don't want you to write all this out. In your sheet, you would say the first possible set is n equals 3, L equals 2,
So you just go
ML equals negative 2.
And then it would be negative 1, 0, and so on and so forth.
Say what again?
And then it would be like 2.
Yes. I'm going to show you the first one and the next. So you're going to see this, then copy and paste that exact same thing. So I'm going to do that exact same thing. So copy and paste. Okay. Copy, paste. Right down here. What changes for the next one?
The ML is going to be negative 1.
Oh, nope, you skipped something first. There are 2 possible options for ML equals
negative 1.
There you go. That's your first option.
I thought we
Sorry. No, my next option is, just like you said.
ML negative 1, and that's
yeah, you get the idea.
Negative 1/2. Okay. So it just wants us to write down that.
Write the sets, yeah.
Okay. And so to get the possible numbers for that, you would just multiply the L to the amount of orientations.
Multiply the L to the orient. The answer is 10. Do you know why? It's
because you get,
No, it's not L. Okay. Sure. I see the rule you just created, but I don't think that is per se a rule, and I want to make sure it doesn't necessarily screw you up. It will screw you up if you try that. It's not L times the number of orientations, it's the number of orientations times 2 for spin. So, for example, if we had done this, but we were talking about this guy right here, 3p instead, then this would be 1, right? And then your number of options obviously get less. That would be negative 1. And if you had attempted to use that rule, that L times the number of orientations, you would get an answer of 3 when the actual answer is 6, because the number of orientations here is 3 times 2, because there's 2 different spins. All right, next question.
I feel like I'm over 8B.
8B?
I think you went over it a little bit.
Yes, we did. Okay, so A, I believe, was just simply the speed of light times 14.4, right? Part B asks you to go figure out how many photons are in a certain amount of energy. So what you do is you use either HF or hc lambda, and that's what I would use because they're giving you lambda, to get the energy of one photon. And then it's simply the total energy divided by the energy in a photon would tell you how many total photons there are. So I am using hc over lambda to get the energy of a photon, right? And then I'm taking energy total divided by the energy of a photon to get the number of photons. So this is, well, hc. Now, do note that the energy, the total energy, is given to you in joules. So I used 3.7, which means when you go get the energy of a photon, make sure it's not accidentally left in EV, because obviously that's going to screw you up. You have to be able to compare the two of them. So using this right up here, a lot of times I like EV, okay, quite frankly, because I think it's nice. I remember that the top of that is 1240 divided by the wavelength of 694.3. So I am getting that. I'm just going to get it in EV. So I have 1.79 EV. But then, to get it in joules, I just remember that 1 EV is equal to 1.6 times 10 to the negative 19th joules. And I get that this is 2.86 times 10 to the negative 19th joules. That comes right down here. So I take my red number, 3.7, divided by that, and I get 1.29 times 10 to the 29th, sorry, not 29th, 19th photons. Yep. Questions, concerns there?
No.
Okay, you want me to talk about C, or are you good?
You said you use because there's one of them has 2 pi r in it, right? So
Well, the one that says diameter right here. So if I draw a picture, it says that the laser has a diameter right here. Come on. The diameter right here, it says of 0.6 centimeters. Now heads up, watch me do this very quickly. 0.6 centimeters, aka that's 0.6 times 10 to the negative 2 meters. What do I need to do to that to get it to millimeters?
from centimeter move.
There you go, same we did earlier. So well, let's make sure you do the work. I do the work every time because you'll mess it up half the time if you don't. Bigger or smaller?
It's getting, well, that's in centimeters, so it's getting bigger.
No, this exponent right here to get to negative 3, bigger or smaller?
Oh, smaller.
Smaller. So what does this have to do?
Get bigger.
So the answer is that is 6 millimeters. Then, if you'll remember, the length of this laser in that amount of time is the answer to part A, whatever your part A is. So I am taking the radius, 3 millimeters, squaring it, times pi, that's going to be that area, times that length is going to give me volume, and then photons per meter cubed is simply going to be my answer to part B, divided by that volume, and that's going to give me my answer in photons per millimeter cubed. Other questions? Are any of you guys sticking around for the meeting after?
We are. Yes, we are.
Yeah.
Okay.
Yeah, probably not even moving, staying right
Fair.
staying straight.
Any other questions I can tackle real quick for Gavin? Gavin's the only one that's using this recording, so.
Oh, okay.
What's up, Gavin? All right. Bye-bye, Gavin.